Okay, the recording has started. Altuğ, the stage is yours. Thank you.
Thank you, Soner, and thanks for the invitation. Unfortunately, in recent times, I don't get too much chance to teach, so this was a great excitement for me. Now, I will be talking about the hadrons, conventional and exotic hadrons. I'm mainly working on phenomenology, and this group, as far as I can tell, is mainly more mathematical physics. So I didn't really know what to talk about, so I kind of included everything I could think of at a certain level. If you have questions, we can just skip some of them, and I mean, just feel free to interrupt me and ask questions. No, so first of all, we will be talking about the strong interactions, and with the strong interactions were first introduced to explain the stability of the nuclei when it was discovered that the atoms contained a very small nuclei formed by positive charges. There should be something to keep them together, and that is what they call the strong interactions. And so in the experiments, we started observing new strongly interacting particles. In general, we call them hadrons. Some were quite heavy, much heavier than the electron, which was the particle known before the nuclei. So they were called baryons, from the Greek baros, which means heavy. And then there were other hadrons that were discovered. They are the bosonic hadrons, and they had kind of an intermediate mass. The first discovered mesons was the pions. They have a mass between the baryons and the electrons, so they were called the mesos, intermediate from Greek. Of course, with new experiments, we discovered mesons that were much heavier than baryons, so this meaning of intermediate and heavy doesn't really make sense at the moment. But the question still remains, what other strongly interacting particles we can observe in the experiment. And this study of the hadronic spectrum had always brought many surprises, like, for example, the discovery of the charmonium. It was first made in hadron experiments, in hadronic collisions. We discovered very heavy, but nevertheless stable new meson. At the moment, one experimental group called it J, another experimental group that observed it called it psi, and nowadays we call it J psi, which now we know that it's a meson made of a charm and an anti-charm quark. It's the lowest, the lightest charmonium that we know. And in more recent times, we have more exotic states, states that we can't really yet understand in terms of our earlier description of the mesons, like a possible pentaquark state in the LHCb, or I mean, this is a three-dimensional plot, let's say, in a sense, and this is probably more clear. All these bumps over here, these are what we call our new pentaquark state. And in a sense, if you think of it, even the discovery of the Higgs, it was in a hadronic collider experiment. And once we have these hadrons, we wanted to know what they are made of. So we had these deep inelastic scattering experiments in which you just scatter high energy electrons, high energy meaning a few GeVs, of these particles and see how they behave. And it was discovered that they behaved in a way that they were that told us that they were actually made up of point-like smaller constituents. So in fact, this kind of gave us a puzzle. On one hand, from the deep inelastic scatterings, we see that these hadrons, these protons and neutrons, were made up of these almost non-interacting point-like particles, because we could explain these deep inelastic scattering as if the electrons were scattered of independent, isolated point-like objects. But on the other hand, we never saw these point-like objects. We only saw the proton and neutron. So these point-like objects, which are called partons, they are almost free within the proton and neutron, but they can never leave the proton and neutron. And these two properties are called asymptotic freedom and also confinement. And with new experiments, after the charm, we discovered the bottom and the hadrons containing charm quark, bottom quark. And in '95, we discovered the top quark. Well, I'm usually bad at dates, but the top quark discovery is something that I can always remember because it was my first year in the university, and it was the recitation hour, and our instructor was Durmuş Ali Demir. So one day he just entered the class. He was quite excited. You know what was discovered yesterday? We were making wild guesses, and he said, no, we discovered the top quark. So nowadays we know that these partons are nothing but what we call quarks and gluons, and we have a theory that describes their interaction, which we call the quantum chromodynamics, or QCD, which is nothing but an SU3 gauge theory, where we have the quarks in the fundamental representation and gluons in the adjoint representations. And these quarks can be in three different, what we call colors, or the color charge. So in fact, that is why we have the SU3, the 3 in the SU3, and there are also 8 gluons that carry one color and one anti-color. Now, the interactions of the quarks between themselves in QCD is described by the exchange of gluons. In fact, the description is very similar to what we have in QED in electromagnetic interactions, quantum electrodynamics. The charged objects, they can exchange a gluon. In QCD, we have the objects that carry the color charge, like here in this process, we have a red, let's say, quark and the green quark. They can exchange a gluon, and the red quark can become a green quark, and the green quark can become a red quark. But we also know that the color charge is conserved. So this basically tells us that this gluon, do you see my cursor, by the way?
Yeah, we can. We
Okay.
can see the cursor.
So if you consider this gluon over here, since the color charge should also be conserved at this vertex, this gluon should contain a red anti-green color. But if the gluons themselves carry color, that also means that the gluons can also exchange other gluons. So here we have a gluon which is colored. Here we have another gluon which is colored, and they can exchange a third gluon, which is a process that is absent in QED. And then we also have a direct interaction of 4 gluons, which is another phenomenon that doesn't happen in QED. And in fact, these self-interactions of the gluons in QCD leads to what is called the asymptotic freedom. At high energies, that is, if the quarks are exchanging very large momentum, or if they are very close to each other, the fine structure constant for strong interaction, it becomes very, very small. So in deep inelastic scatterings, since we are looking at scattering by very high energy electrons, the interactions of the quarks at those scales are very weak. So that is the reason why we observe the partons as if they are not interacting in deep inelastic scattering processes. Well, confinement is somewhat a bit more complicated, although we do believe that QCD is confining, there is no definite proof for that. So here we have on the left, you see a simulation, a lattice QCD computation, where you actually see this tube forming between one quark and one anti-quark. And this tube, within this tube, we have the color, electric, and magnetic fields. They concentrate within this tube. So what this, and if you try to separate these quarks and anti-quarks, what happens is that the energy stored in this tube increases linearly. And if the energy becomes sufficiently large, we expect this flux tube to break. So to minimize the energy, rather than extending the flux tube, we just get the energy is converted into a new quark anti-quark pair. So if you have these 2 quarks, you try to separate them. At the end, you just have a quark anti-quark pair in both of your hands. You cannot get a single quark. So this is what we believe is happening. But as I said, there is no definite proof in QCD. Okay, so we were looking at the hadrons. So what are the possible combinations of quarks and gluons? In fact, color confinement allows us to classify, in a sense, what are the possible combinations. So color confinement states that only colorless states can be observed. So the quarks, they should come together in such a way, quarks which are colored objects, gluons which are colored objects, they should come together in such a way that they are colorless, or in a more mathematically precise terminology, let's say they are invariant under this color symmetry. So what are the options we have? The simplest we can think of is if you take a color and an anti-color, the charge of an anti-quark, you can create a colorless object. So you have a 3, which is a quark, and a 3 bar, which is the anti-quark. So if you just bring a quark and anti-quark together, you do get a state which is singlet under this SU3 symmetry. So it is a colorless state. So this is very similar to, let's say, for example, the hydrogen atom. So in the hydrogen atom, what you have is you have an object which is +1 charge, another object which is the anti-+1 charge, let's say, the -1 charge. So you bring them together and it becomes a neutral object. So these very simplest states are very similar to the hydrogen atom in that sense. Of course, this 8 doesn't exist in electrodynamics. Now, the second simplest choice would be just to bring 3 colors together. In fact, this is the reason why this charge is called the color charge. Just like if you just bring red, green, and blue light together, you get white light. If you bring 3 quarks together in a suitable combination, one of those combinations is singlet under the SU3 symmetry. So it is colorless. It doesn't change under color transformations. So these two are 2 of the simplest things that we can think of, simplest colorless combinations. And of course, you can just put these objects together among themselves. You just bring 2 baryons together or 2 mesons together, a baryon and a meson together. You can form other colorless objects. So all this description, if you put it on the lattice, do the lattice computations, for example, here I just, as an example, I just wanted to show the baryon computations. So the single heavy baryons, these red lines are the experiment, whereas the blue lines are the result of the computation based on QCD. And so as you see, in all the observed baryons, the agreement is almost perfect. So you see here, the parameters we have are, let's say, the 6 quark masses and 1 coupling constant. Those are the only parameters we have. And we have many other predictions made by the lattice QCD. And these 7 parameters, they can also predict not just these baryons, but the mesons, the double heavy, single heavy baryons, mesons, etc. Now, what about the mesons? There are various descriptions of mesons. You can, of course, use the lattice QCD to describe the mesons, but an intuitive description would be what is called the non-relativistic quark model. So just as I stated before, the mesons are very similar to the hydrogen atom. So the simplest thing you can do is just treat it like the hydrogen atom or any other atom. So you have 2 charged objects. They should be interacting by some kind of a potential. They will be rotating around themselves. And so how do you describe this? Well, you can write the Schrödinger equation. You need to choose a potential. Well, we don't know what exactly the potential is, but we do know certain limits. Like from the asymptotic freedom, we know that at very small distances, they almost behave like a free particle. So because of the running coupling constant becomes very small. So the dominant contribution should be 1 gluon exchange, just like in the case of quantum electrodynamics, where we have 1 photon exchange. So the potential will be just 1 over r times the fine structure constant of color charge. On the other extreme, if the separation is large, we know from lattice computations, at least, that the flux tubes do form. And if there's a flux tube forming, if you increase the separation, the potential energy, in this case, it will be the energy stored in this tube, it will increase linearly. So we know that at large separations, the potential should be somehow increased linearly. And the simplest potential you can write that satisfies these 2 asymptotics will be just their sum. So we have the Coulomb part and the confining part. And here this K is just some parameter, which can be determined also from the lattice, or it can be fitted to experiment. So just like in quantum mechanics courses, when you study hydrogen atom, if you want to fine-tune your model, you add the spin-orbit couplings, spin coupling, you can add the relativistic corrections. And but these corrections, I mean, neither the spin-orbit coupling or the spin-spin couplings, they don't introduce additional parameters. And this is another sample of what you obtain about the spectrum of these particles. So this is the charmonium. So these are mesons which contain one charm and one anti-charm. So there is this line over here, which is called the open charm threshold. Essentially, if you have a charmonium that is heavier than this line, it can decay into two D mesons, each one of which contains one charm or anti-charm. So that is why it's called the open charm threshold. And you see that below that threshold, again, the agreement with experiment is almost perfect. And in this model, in this very simple model, the number of parameters is something like you have 10 parameters in total. And the number of states that you can explain using this 10 parameters is in hundreds. Well, this is just one of the sample. Now, the problem arises what happens above this threshold. So you see, if you look at over here, well, there are certain states over here which are not yet observed. You can say that, well, maybe if they are observed, they will agree with it. But here you have many states, like these two red ones, let's say, some new states that we observed in experiment. There is no prediction for that. This model, although it works almost perfectly below this threshold, but if you go above that threshold, the agreement with experiment becomes highly problematic. So this is something we should understand. Why does it happen? Now, before I continue, I would like to just clarify one, let's say, terminology. When we talk about the hadrons, we usually say that, for example, for the proton, we say that proton is a baryon made up of two up quarks and one d quark. Or when we talk about the mesons, pi plus, we say it's a meson consisting of an up quark and an anti-d quark. Well, this terminology is not really correct, in the sense that, okay, for example, if you look at the proton, yes, proton does have the quantum numbers of a state made up of two up quarks and one d quark. But if you would look in the proton, you would also see strange quark, anti-strange quark, anti-up quark, etc., all the other quarks, and even you would see the W meson, etc. And in fact, if you talk with your colleagues working in CERN experiments, they have all these parton distribution amplitudes. They talk about the gluon content of the proton or the anti-up quark content of the proton. So that I will still stick with the wrong terminology, but whenever I say that it's made up of an up and a d and an anti-d quark, I just wanted to clarify that point. So here, for example, if you look at the pi plus, it is, as a quantum mechanical state, it is actually a superposition of many components. So you have yes, you do have a state that only contains an anti-d and an up, but you also have states that contain gluon, you have states that contain 4 quarks. This expansion is actually infinite. So if you go back to our problem of what happens above the threshold, why do we have such a disagreement between the non-relativistic quark model computations and the experimental observations? Well, there are many hypotheses about that. Well, some people claim that, okay, the observed states are conventional mesons, but the potential quark models, they're just models at the end of the day. They are not the exact theory, so they do fail. And so the disagreement is not due to the nature of the meson, but rather due to the failure of the potential quark model. So these people still claim that it is good enough to describe these mesons as, let's say here we have the pi, for pi plus, the first term is good enough. Or in the case of the charmonium, CC bar component is good enough. Or there are some people who claim that some of these states can be molecules, meaning they are bound states of colorless objects like two mesons or two baryons, or you take one baryon and one meson. Well, this is not so much, well, this is interesting, but not as interesting as, let's say, what's usually called genuine tetraquarks. So they cannot be split into colorless objects. They are very compact objects. Maybe some of them are these tetraquarks and pentaquarks. Well, there are the other possibilities. We can talk about the hybrids where we have an additional gluon in the system, or glue balls, which are made up of mainly only gluons, no quarks, or they can even be more exotic states. So this is here you see hundreds of examples of baryon molecules. All the atomic nuclei are actually baryon molecules. So, and they have been studied in nuclear physics, but they're not so interesting, let's say, in particle physics. Now, before continuing discussing what other structures we can construct, what other colorless structures, let me also introduce the concept of diquarks, which will allow us to generalize all these combinations. Now, a diquark is mainly, you see, here we have if you bring two quarks together, not one quark and one antiquark, in a suitable combination, they become a 3-bar, which basically tells me that in this configuration, these two quarks actually behave like a single antiquark in terms of its color charge. So one anticolor, if there's an anticolor in my system, I can replace it by two colors. And in fact, the same is true for the colors. If I have one color, I can replace it by a suitable combination of two anticolors. And yes.
I'm sorry to stop, but this is only true for SU2, right?
No, this is true for SU3.
Oh, so yeah, sure, SU3.
Yes. Only, well, if you have SUN.
Rank 2. Yeah, U2 or SU3, so yeah.
So if you have SUN, in that case, N-1 colors behave like one anticolor, or N-1 anticolor. You see here, this 2 is just 3-1.
Yeah. Okay.
And in fact, in SUN, if you want to talk about the baryons are made up of not 3, but N quarks. So you just bring N quarks together to form a colorless object. If you just remove one color, what remains should be an anticolor.
Sure.
That's also another reasoning you can use.
Thank you, sir.
So these diquarks basically allows us to construct some possibilities for multi-quark states. So you start with a meson, which is a quark. Here it's just the red and the anti-red. Quark and an anti-quark. Okay, so you can replace, without changing its color properties, you can replace the anti-quark by two quarks. So this way you can construct a baryon here. You can take this baryon and replace this red quark by a suitable anti-diquark. Still color doesn't change. We started with a colorless object. We still have a colorless object. This is what is called a genuine tetraquark. So it cannot be broken into two colorless objects. Or
Hocam,
yes.
I'm sorry to interrupt. May I ask a question here?
Sure.
Being able to replace a color with two anticolors or vice versa, can we, or is it possible to make use of this to convert any kind of state in the superposition of a hadron state into a conventional quark model state, or can we classify them at least? Is there something like that? I mean, for example, a tetraquark state can be expressed as a QQ bar state from this perspective.
Or
is this a logical question at least? I mean,
I don't know whether it will give us any new insight, but just that you ask about classification, for such a classification could be possible. So we are talking about these meson molecules, tetraquarks, pentaquarks, etc. What about a molecule of a tetraquark and a conventional meson?
Mm-hmm.
I mean, such states are not looked for. Are there any candidates? None that I know. Will they be discovered? Probably eventually. I don't know.
So if there are tetraquarks, they should also exist.
Sure. You see, one question we have is what are the possibilities? So these are just some of the possibilities. These are not molecules. The other question is, do they really exist? And if they exist, how can we tell that they are actually a tetraquark or some other state? You see, if you look at it from a perspective of an experimentalist, what they measure is actually quite limited. They just measure momentum, energy, charge, spin, and well, basically that's it. So just using those information, how can you tell a tetraquark from a conventional meson, for example?
So we are only bound with the quantum numbers of the states then.
Well, they can be one way of separating some of the exotics from the conventional counterparts, but not for all of them.
Thank you.
So for example, in terms of the color quantum number, these are all identical.
Mm-hmm.
Okay, so thanks also for the question. How can we distinguish them? We should make some predictions about these models. For example, if we have a tetraquarks, you see, when I was talking about this flux tube, I was saying that if you just stretch this flux tube, eventually you would get two mesons in both of your hands. Well, similar things can happen over here. If you just stretch the flux tube in this diquark, let's say, it can stretch on its own if its energy is large enough, or you can just hit it with, I don't know, an electron and just push this green quark. And in that case, this colored flux tube will also stretch. But if this flux tube breaks down, you end up having a meson, a tetraquark and a meson. So if this tetraquark picture is correct, you should have decays where a tetraquark decays into a tetraquark and a meson. Or you can have this intermediate flux tube stretching. It can create a quark-antiquark pair. So you end up having a tetraquark decaying into two baryons, of course, assuming the kinematics allows it. So you should be just saying that, okay, we have this tetraquark. It's possible that this state might be a tetraquark is not enough. In that case, you should also explain, do you see these decays? If not, why not? So this is just a direct consequence of your model. If you cannot see the consequences of your model, then you should just throw it away. Okay, some of the electric charges that we can use to separate conventional hadrons from non-conventional ones, the electric charge. If you consider a conventional meson, it is a quark and an antiquark. The quarks have charges plus minus 2/3 or plus minus 1/3. So if you just bring a quark and an antiquark together, the only possible charges are plus minus 1 or 0. So if you ever observe a meson with a charge of plus 2, let's say, then you are definitely sure that it is a non-conventional meson. Well, the same thing holds for the baryon. So if you observe a baryon which has a charge larger than 2, then you are definitely sure that it is it's not a conventional baryon. And another thing is for example, quarkoniums, which are moniums, but monium, they are easy to identify. And one of their electric charge is 0 because these quarkonium, they carry a quark and its antiquark. These are also easier to create because you can create them from photons in electromagnetic interactions. So if you create these quarkonium and you see that they carry an electric charge, one example is so-called ZC plus. It's a charmonium with a positive charge. In that case, we definitely know that it's a exotic state, not a conventional one. Another quantum number we can look at is the total spin J, the parity P, and the charge conjugation, charge parity C. So if you just take a quark and an anti-quark for mesons, for example, the parity is determined by the angular momentum of these quarks, quark and anti-quark. The C parity, well, not all mesons have a C parity, but if you have a meson which has a C parity, it is given by -1 to the angular momentum plus the spin of these quarks. So you can just tabulate the possible angular momentum quantum number. It starts from 0, it goes up to infinity. The spin, since we are talking about 2 spin 1/2 particles only, so it can only be 0 or 1. So for the JPC quantum numbers, you have all these possibilities. But for example, if you look at the scalar ones, you have a scalar with negative parity and positive C parity, and a scalar with positive parity and positive C parity. But you never get a scalar with a negative parity and a negative C parity. So these quantum numbers are not allowed for a quark anti-quark state. So if you ever observe a particle which has these quantum numbers, then you can be definitely sure that if you write its quantum mechanical state, the QQ bars component should be absent because it doesn't have the compatible quantum numbers. You can have, of course, quark, anti-quark lone, or 4 quark states, various 4 quark states as a meson molecule, 4 quark state as a tetraquark, etc., or a baryon molecule, but you are definitely sure that it is not a conventional meson. Well, then we have the questions. Some of them we had already asked. Do they exist? Okay, we looked at confinement. Confinement limits the possible combinations of quarks and anti-quarks, and but still, do some of the possibilities, like 4 quark, 5 quark, 5 quark states, do they exist? Do they have the same quantum numbers with the conventional hadrons? You see here in this table, okay, we know that if there is a 0 minus meson, if we observe it in experiment, then we are definitely sure that it is a exotic meson. But if you observe, let's say, a 1++ state, in that case, this 1++ quantum numbers are consistent with assuming it's a CC bar, charm and anti-charm meson with an angular momentum 1 and total spin 1. But it is also consistent with a D and D star, a bound state of D and the D star meson, which would be an exotic state. So exotic states, they don't have to have exotic quantum numbers. Some of them would have the quantum numbers of conventional states, but then how do we tell them apart? If you remember in the table about the non-relative, in the chart I show about the non-relativistic quark models, above the open charm threshold, there was disagreement between the experiment and the observations. And one possible explanation is that all those states, they have the quantum numbers of a charm anti-charm state, but one possibility is they might be exotic. And so if they are exotic, what should be their properties, and how can we tell them apart? Okay, another just, let's say, interlude before I talk about, I will be talking about theoretical models. So I would like to talk about what we mean by resonances, because whenever we are talking about these exotic states, most of the time you will hear people call them resonances. So we have bound states, which are stable particles. They are actually the eigenstates of the Hamiltonian of nature, let's say. And in fact, if you think about it, the only bound states that we have, only genuine bound states we have, are the ground states of non-radioactive atoms. All the other bound states are unstable. For proton is the ionized hydrogen. If you think about the neutron, it's unstable, it decays weakly. If you consider the pion, pi plus, pi minus, pi zero, they decay either electromagnetically or weakly, etc. They are nevertheless eigenstates of QCD, but they are not stable particles. Now, these eigenstates of QCD, they are stable for a very long time compared to the natural, let's say, time scale. For example, neutron decays in 15 minutes if you have an isolated neutron. So that's like infinitely long. It lives forever almost, compared to the typical lifetimes. Raw meson, for example, we easily see it in experiments, but it's not a stable particle. It's what we call a resonance. Now, if you look at the typical time scales for pi plus and pi minus, it can only decay through weak interactions. So it decays a very long time, 10 to the power minus 8 seconds. If you consider the pi zero, it decays electromagnetically. The time scale is, its lifetime is 10 to the power minus 16 seconds. And if you look at rho, which decays strongly, it decays in 10 to the power minus 24 seconds. Unless this rho is moving at speeds very close to the speed of light, very close to the speed of light in typical experiments, the distance it will travel before decaying will be less than the size of an atom. So there's no way you can see the rho in your detector. So these resonances, you don't observe them directly in your detector, but only indirectly. So what do I mean by observing them indirectly? Well, let me just skip these. So if you create a resonance, you just collide two particles, for example. You create a resonance in this process, and this resonance decays very fast. And so it decays into two, in this example, let's say two different particles. You can calculate the cross-section for this process, and this cross-section will be proportional to such a factor due to the presence of the resonance. And if you plot it, this basically gives you an enhancement when the energy is close to the mass of your resonance. So these are the peaks. These peaks tells us that we actually have created a resonance in our scattering process. So this is one of the examples of what we experimentally observe. So here the process was, here this resonance over here was actually the discovery of what's called X3872, the first candidate for an exotic meson. And it is the meson that I'm mostly working on. But still, okay, the resonances do create peaks in certain scattering processes, but unfortunately, we cannot also say the reverse. The peaks do not always correspond to a resonance. So this is just a theoretical model in which there's no resonance, but especially if you are very close to a threshold, you get some enhancements without a resonance. And well, this is on the right-hand side, you have the theoretical model. If you include the experimental uncertainties in this computation, you get a very nice looking peak, which is not a resonance. So this is kind of the complicated part from an experimental perspective. So if we see some peaks, how do we know that they are resonances? Now, I would like to talk about some very simple theoretical models that would allow us to describe these resonances and allow us to make predictions. So you see, this is probably the simplest model you can think of in the diquark picture. So just imagine this, you have two diquarks made up of, one made up of a quark and an anti-quark. In this particular case, it's a charm quark and a light quark, U or a D. Another one containing an anti-charm and an anti-quark. So the simplest thing one can think of is that, okay, these two things they have their own mass, these diquarks. So it's the first term. We have two diquarks. One diquark is the anti-diquark of the other one, so they should have the same mass. So that's why we have twice the mass. And in these within these diquarks, we have objects that have spin. So we can add spin-spin interactions to this model. So we have the spin of the light quark in this diquark interacts with the spin of the charm quark in the diquark. And again, since they are just diquark, anti-diquark pair, they are the anti-diquarks of each other. The coupling between the spins should be identical. So that's why we just have a single additional parameter over here. Of course, you can also think of coupling between a quark over here and the quark, anti-quark over there. But you expect these diquarks to be very compact. So the quarks in the diquarks will be very close to each other, whereas these two the quarks in different diquarks will be separated by a larger distance. So you can just neglect that interaction. So here we just have some spin interactions within the diquarks, and not you just ignore the spin interactions between inter-diquarks. So this would be a very simple model of a tetraquark made up of two diquarks. So of course, if you have such a model, to identify these parameters, you should also identify some mesons. What are the possible observed mesons that can fit in this picture? Well, X3872 is one of the most popular exotic state candidates, since we have the most data on that. And they can just identify these spins, S and S bar. They are the total spins of the diquarks, which can be 0 or 1. If we just pick up some suitable observed mesons like X3872 or Z3900 and Z4020, well, you have these three mesons and two parameters. Well, you can fit them. You can determine the two parameters, in fact, just using two of them, and then determine the other one. And well, these are the parameters. Then if you determine these parameters, then you can make predictions. You see, if you just have 4 spins can combine in 16 different possible combinations. Some of them will have identical total spin, so it won't be easy to separate them. But you can just, by just looking at picking up 2 mesons, you can predict the other mesons in this multiplet. And in fact, they have made predictions which are to be compared with future experiments. Let's say there should be 2 states which are almost degenerate with this Z4022, and with these value, you can have the lightest scalar should have such a mass. Now, just determining the masses are also important from an experimental perspective, because I mean, experimentalists have this access to all very large energy range. So we should also be telling them in which energy region they should look for. So here, so we have some guiding principle for our experimental friends. Now we can also add the L equal to 1 model. You can just generalize this. Well, if you have the L is equal to 1, there will be a contribution due to the angular momentum. If you can just imagine this angular momentum as these diquarks rotating around each other. So they will have some additional energy due to this rotation. Well, you can have some coupling of this angular momentum of the system to the total spin of the system. And just as before, you can have spin-spin interactions within the diquark. So again, you have a very simple model with 2 more additional parameters. And we already have certain candidates for this system. So we have the candidates, we identify the parameters, and then we look for the predictions. So we said that if you make a diquark model, this model has certain predictions, which is a nice property of the model, but it also means that these predictions should be checked with experiment. And if they don't agree with experiment, you should just throw away your model. And in fact, one criticism of this diquark model when it was first proposed to explain these exotics was that it predicts many exotic states. And at first we only had a few of them, but with time nowadays we are discovering new exotics. I don't know, there's a new news more or less one new exotic every month. So the numbers are increasing, which is a plus for this diquark picture. But of course, this model has the limitations. The parameters, we are basically fitting them. So for a deeper understanding of their structure, we should be able to kind of drive them from QCD. So that is our fundamental interaction of the fundamental theory for describing the interactions of quarks. And how do we, okay, the masses can be predicted by this very simple model, but what about their decay rates? It doesn't really allow us to calculate the decay rates and interaction with other states. And you see, if you look at these models, okay, in this simple model, there is the additional angular momentum, but about radial excitations, radial motion, there's no such a description within this model. And so it kind of limits its applicability. There are certain attempts where people just start with this diquark picture, where you have these two diquarks, they are very compact objects, and they treat these diquarks as point objects, and then write a non-relativistic quantum model, Schrödinger equation, and try to calculate the various possible other states and its interactions and decays. Okay, so if we go to the meson molecules, and well, there's a nice framework to describe these meson molecules, so-called the effective theories. Now, I will be talking about X3872, one of the supported model, well, one of the models which is studied by many people, is to describe X3872 as a meson molecule, where it's made up of a D meson and a D star meson. A D meson is a charm quark, is made up of a charm quark and then anti-up or anti-down quark, depending on its electric charge. And it is a scale, its total spin is 0. Whereas a D star is, its total spin is 1. They have 0 angular momentum between this charm quark and other light quark. Angular momentum is 0. Their total spin of these quark and anti-quarks can be 0 or 1. If it is 0, it is D. If it is 1, it is D star. Now, if you look at the X3872, its mass is very close to the sum of the masses of D0 and D0 star. In fact, this is one of the motivating observational measurements that motivates this molecular picture. Because if you consider the mass, what we call the mass is actually the minimum energy that this state can have. So if you just put a D meson and a D star meson together, and if they have a binding energy, the total mass of the system would be lower than the masses of each one of these D and D star by the binding energy. The total energy is lower than the sum of the mass energies. And since that if within this picture, the binding energy actually turns out to be much lower than 1 MeV, which is, if you compare it with the mass of the D meson, which is larger than 1 GeV, it's a very small binding. It's just like if you look at the hydrogen atom, the mass of the hydrogen atom is not equal to the mass of the proton and the mass of the electron, but the mass of a hydrogen atom is equal to the mass of the proton plus the mass of the electron minus 13.7 electron volts, which is the binding energy. So you have these two D and D star mesons. They are somewhat in a bound state. So the simplest thing is write Schrödinger equation. So you have the energy, the Hamiltonian of a D0 and D star 0 will be sum of the masses plus the kinetic energy of this two-body system. Well, of course, the X need not contain only D0 and D star 0. It can also have its charged analog. So you can also write that charged analog where you have a D plus and a D star minus meson. And then you have the kinetic energy of these charged D mesons. So this is essentially the first part of this Hamiltonian is a, you can think of it as the kinetic energy plus the mass energy of a two-state system, where each state is actually a three-dimensional Schrödinger equation in a sense. Here, when I say state, it's either d0, d star 0, or d plus, d star minus, or the charges are reversed. And then these d mesons are interacting through some potential. So which we also don't know, we should somehow model it. Now, if you, before even going and trying to solve this, if you look at the asymptotics, the wave function, whatever wave function you obtain at the end, will be decaying exponentially. And this lambda over here would just give you a sense of the size of this system. And lambda just turns out to be 3 to 5 femtometers. Well, depending on how you interpret the size, you can say the size is 10 femtometers or 3 femtometers. Well, the main thing is this is huge. Huge because if you compare it with our conventional mesons, the conventional mesons or baryons, they are just 1 femtometer or even smaller. So here, if this is a molecule, this is a really huge molecule. Well, if you look at the potential, what will be the potential? Well, the simplest, well, there are a couple of things we should keep in mind. The binding energy is very small. So these are moving very slowly, which means that they are not exchanging much energy. The momentum exchange is very small, which means, well, the corresponding de Broglie wavelength will be very large. They will not be able to tell whether the other D meson is a point object or not. And in fact, since the momentum is very small, this matrix element, you can just approximate it to be a constant, because the only thing contribution will be from the very small momenta. But then you get other problems within this picture, because if you assume a constant potential in momentum space, that means you have a Dirac delta interaction. It's a contact interaction. Well, the problem with this Dirac delta interaction is that if you study the Dirac delta potential in 3 dimensions, it doesn't have a finite energy bound state solution. But then what is usually done is you just regularize the interaction. You put some cutoffs in your theory. But when you put these cutoffs in your theory, the potential becomes a non-local potential. And it's hard to distinguish what predictions are due to this introduced non-locality, what properties are from the actually described the system you have. Now, one thing you can do to improve is also to include other interactions. If you want to introduce other interactions in your system, you can try to write down a field theory. Well, the de Broglie wavelength of these D mesons will be very large. So nothing in your system can actually see the internal structure of your D mesons. But that means that you can just treat them as point objects. So you have these point objects, which you can treat as your fundamental objects in your field theory, which they will be interacting with each other. So you write it's the kinetic energies. No, sorry, the first line is the kinetic energy, the mass of the scalar D meson. The second line is for the vector D meson, and you can just add as many interactions as you want. Well, then the problem is there are too many parameters here. There are various tricks to go around them. Symmetry is one of them. And we have two, at least for this system, we have two important symmetries. One is the isospin symmetry, which basically tells us that if you just exchange up and down quark, nothing should actually change. If you think about the electromagnetic interaction, this is just doesn't make sense. The up and the down quarks, they have different charges. So if you change the up and the down quark, all the electromagnetic properties would change. But if you are looking at strong interactions, if you are studying processes that go through strong interactions, the electromagnetic interactions are very small. So electromagnetic interactions are basically a very small symmetry breaking phenomena. So In terms of QCD doesn't really distinguish between an up quark and a down quark, except then through its mass, and their masses are almost identical. And in fact, they're almost massless. So exchanging U and a D quark exchanges a neutral D meson, makes a neutral D meson a charged D meson, so which basically tells us that, for example, these mass terms for the neutral and the charged D meson should be the same. You get some similar relationships for the interaction terms that lowers your parameters. Another symmetry that is quite often used in the study of these exotics is so-called the heavy quarks symmetry. What happens is if you have a very heavy quark, and in fact, if you take the limit that it is infinitely heavy, it is spin basically decouples from your dynamics. It doesn't really affect anything. So it doesn't affect the mass of your particle. Like if you look at the D and D star meson, the only difference between a D and D star meson is how the spin of the heavy quark, the charm quark, is combined with the spin of the light quark. But if you just decouple the charm quark spin, the only thing left is the spin of the light quark, and the spin of the light quark in both D and D star meson should be the same. So D and D star should have the same mass. And if you actually look at the masses, they are very close to each other. And the difference in their masses actually gives you an idea about the breaking of this heavy quark symmetry. And not just the masses, their interactions should also be related by this symmetry. And so that also gives you relations between these lambda parameters. I'm kind of running out of time, but I'm also about to finish my talk. Well, another method that we use is QCD sum rules and lattice QCD. I'm not going to go into too much detail, but the idea is we just try to calculate such a correlation function. Now here, this J's are composite operators, which create quarks and gluons or whatever you put in it from the vacuum. So here, what we are actually looking at is, in fact, in a sense, kind of, we are doing an experiment. We are just putting quarks and gluons, whatever, depending on this properties of this operator J. We are looking at quarks and gluons at some space-time point and see how they scatter off each other and evolve to the space-time point X. And well, if you just have eigenstates, energy eigenstates, you end up having this correlation function basically has poles. If they are not stable, but they are resonances, they will not diverge, but they will have some width. They will give us some peaks. And so if we can somehow calculate this correlation function, by just looking at the poles, we can determine where these particles are. We can determine their masses. Now, the problem is, how do you calculate these correlation functions? Well, there are various methods. One is the numerical computation. That is what the lattice people do. They just put this QCD on the lattice, and they try to calculate this correlation function. And from this correlation function, they try to extract some of these poles. Well, here you have, if you look at this line, actually you have infinitely many terms over there. You might have infinitely many terms, and you cannot extract all of them. But at least for the ground state, you can just convert this polynomial suppression to exponential suppression. In fact, on lattice, this is what they directly calculate. And you can see that the dominant contribution here will be from the state that has the smallest mass. So you can extract the mass and try to say something about the structure. Okay, so I think I will just end over here. I just wanted to give a brief overview of what the problem is, what the problem we are facing at, some of the theoretical tools that we are using. And hopefully I could also convey the message that the hadronic spectrum is still a rich subject where there are many things that we are trying to understand. And in a sense, you all hear about these talks about new physics, in a sense that is the only new physics we have. So thank you for bearing with me up to this time.
Thank you very much, Hocam. Well, indeed, I mean, you could use a bit more time, but it seems we got the main idea. So is there any questions? And as I said, I mean, please, if you have any other points to make, so we could use a bit more time.
Well, Gökhan, I don't know if you were in the department at those times, but at certain point in the department, I remember giving 3 seminars, 3 hours each to just finish my talk. But nowadays, it becomes too tiring.
Okay. Then thank you very much. So is there any question?
Well, let me also go back to my first slide. If you have any questions that you would like to ask, you can just send me an email.
Okay, then maybe we can just start the break and continue with informal discussions.
Hocam teşekkürler.
Kayıt devam ediyor mu Gökhan?
Evet, bir dakika. Soner kısa bir süreliğine ayrılmıştı da hocam. Ben de kapatamıyorum kaydı. Keseriz ama merak etmeyin.
Yani 1,5 saat, 1 saat 15 dakika mı süre vermiştiniz? Yok, 1,5 saat.
Aslında buçuğa kadar vaktiniz vardı. Biz 15 dakika ara verecektik. Şimdi yarım saat aramız var.
1,5 saat diye programda görünüyor. Ona göre ayarladım. Yoruluyor insan artık.
Pardon, merhaba.
Performansım düştü.
Soner, kaydı ben durduramadım. Sen durduracaksın.
Pardon, durdurayım elbette.
Hı hı.